Hello there, this is True Socrates. Welcome to today's video where we're going to talk about approximate integration. And as the title says, there are two methods which we are going to focus on. They're called the trapezoid method and Simpson's rule. So if we are going to compute an integral, a definite integral, the main problem is that, well, we need to find an antiderivative if we want an exact answer. So in the past, 5 or 6 videos, we talked about methods, powerful methods, which allow us to find an antiderivative, like integration by parts, trig integrals, trig substitution, partial fractions. Okay, maybe 4 videos. But of course, before that, we talked about a host of integral formulas involving e to the x, a to the x maybe, ln of x. So we definitely expanded our vocabulary of antiderivatives from beginning calculus, where we basically had the power rule, integrals of some basic trig functions, and of course the substitution principle. Okay, so the main obstacle in computing the exact value of a definite integral is finding this antiderivative. Okay, can you think of a function, capital F, whose derivative is the integrand, little f of x? Okay, try it on this horrible function. We know how to integrate cosine x, but cosine 1 over x, yeah, good luck with that. You can try a u sub. Obvious trial is u equals 1 over x. Du is negative 1 over x squared dx. So solving for dx, you'll need negative x squared du. But if u is 1 over x and x is 1 over u, so now you have 1 over u squared, or negative 1 over u squared cosine u. And yeah, good luck with that as well. However, technology is good for at least one thing. In this case, we have a definite integral. So Maple does have the capacity, the capability of approximating an integral. And all I have to do is click on this button. Whoops, not that one. I have a little space there. So let me grab the whole thing. And there we go. So that definite integral is approximately 3.834. If we try to ask for an antiderivative, so I'm going to need the integral symbol, which is this one, and I will copy this, and we can ask, okay, how about an indefinite integral? What you got? Nothing. Okay, so even Maple doesn't have an antiderivative for cosine 1 over x. So that's too bad. So we're going to study two methods which will allow us to approximate the value of a definite integral, come up with an answer such as this, and in the next video, we're going to learn the accuracy of these methods. We come up with an answer, how much can we trust this answer? Is it accurate to 4 decimal places, 10 decimal places? We will find out in the next video. Okay, so here's an overview of the trapezoid method. We will start by subdividing the interval of integration from a to b into n subintervals, and we will divide them into an equal number. Each piece will have the same size. So the width will be the width of the interval, b minus a, divided by the number of pieces that we want, which is n. Okay, so we've seen this symbol before in basic calculus, where that is how we subdivide the interval into n equal pieces in preparation for, let's say, the left endpoint or the right endpoint or the midpoint approximations. Okay, so based on this width, we are going to find the endpoints of the intervals, the subintervals. So the left endpoint A will be x0, and then we move to the right by delta x, that's x1, move one more time to the right by delta x, that's x2, until we reach the right endpoint, which is B. Okay? So instead of approximating the integral with a rectangle, which is what we do with left endpoint or midpoint approximation, we will use, as the method implies, a trapezoid to approximate the region, the area within xi and xi plus 1. Okay, so basically we are going to connect 4 points. On the bottom, we have xi 0. To its right is xi plus 1, 0. Above xi is xi f of xi. And above xi plus 1 is f. I'm missing an f there. F, oh no, I'm sorry. It's in the y-coordinate. Xi plus 1, f of xi plus 1. So we are going to use this idea to compute this definite integral, approximate it. But first, let's go to GeoGebra and find out, okay, what is going on over here? How are we going to do this efficiently? All right, so I found this diagram on the internet. Why not? First, let's review how to find the area of a trapezoid, okay? So it's almost a rectangle, except of course we don't have straight sides on the left and right. We do have parallel bases, okay? So the bases are denoted B1 and B2, and the distance between the two parallel bases is the height of the trapezoid. So it's basically take the average of the two bases, B1 plus B2 divided by 2, and multiply by the height, okay? So it's almost the area of a rectangle. If this were a rectangle, then B1 and B2 would be exactly the same, and the average will be B1 or B2. Okay, so it's practically the area of a rectangle. We're going to use this in our method because our trapezoids will appear, but they will be vertical, okay, as we are about to see in GeoGebra. All right, so I started out this little diagram. I have this arbitrary function over here, and we're going to demonstrate how the idea behind integrating, let's say, between, I think, 2 and 10, okay? So to keep it simple, we will divide into 1, 2, 3, 4, 5, 6, 7, 8 sub-intervals, and we said that we are going to find the value of the function at each of the endpoints, okay? So I have that over there, okay? So between 2 and 10, I am plotting the point above each of the integer coordinates, okay? So the y-coordinate at each point, so we have those points, and we said we are going to approximate the region between two consecutive points using a trapezoid, okay? So I have, let's see, is it this one? Yes, that one. Okay, so you can see that at least for the first 1, 2, 3, 4, 4 sub-intervals, the trapezoids are almost a perfect fit, okay? The area within the trapezoid is almost equal to the area bounded by the region, by the curve, okay? Here, it's not so good, okay? You can definitely see that there's a gap between the trapezoid and the function, okay? So we said the area of a trapezoid is the average of two bases multiplied by the height, okay? So the height in this case is delta x. In this case, delta x equals 1, but in general, delta x can be any number. It could be 1/2 and so on. Of course, it has to be positive. Okay, so we called the left endpoint x0, followed by x1, x2, x3, x4, x5, x6, x7, and x8. Okay, so 8 sub-intervals. And because we start counting at 0, x0 is the left endpoint, we finish with x sub 8, the right endpoint here being 10 in this example, okay? So the area of the first trapezoid will be the average of y0 and y1 multiplied by the height, which is delta x, okay? So yes, of course, all the trapezoids will have the same width, or in this case height, I guess, except it's lying down, or in this case, I guess, standing up. So all of them have width or height delta x, depending on how you want to look at it. For the second trapezoid, the bases are y1 and y2. So we want the average of y1 and y2 multiplied by the same height, delta x. Okay? So notice, y0 and y1, y1 and y2, then we have y2 and y3, and so on. Okay? So hopefully you see the pattern, and let's go back to our workroom and let's figure out the formula. Okay, so we have 8 trapezoids. In general, we're going to have n trapezoids. The area of the first trapezoid is 1/2 the average of the two heights, two bases rather. So we said we have y0 corresponding to x0 and y1 corresponding to x1. The value of the function at those 2 points, multiplied by the height of the trapezoid, in this case the width, which is delta x. Okay, so that's the first trapezoid. Second trapezoid will have a similar area. The height is definitely the same, but this time the bases are y1 and y2. Okay, remember the pattern. So next we have y2 and y3, and we will keep going up, whoops, wrong punctuation mark, all the way up to the last trapezoid. The right edge, the right base will be y sub n, and before that is y sub n minus 1. Okay, so what do we have in common? Well, everyone has a 1/2 and everyone has a delta x. So we can factor that out. We will get 1/2 and, whoops, not there, over here, 1/2 and delta x. And from the first trapezoid, we have y0 plus y1. Okay? And then from the second trapezoid, we have y1 plus y2. From the third, we have y2 plus y3. And we keep going on until we reach, not the 1/2, until we reach yn minus 1 plus yn. Okay? But just to emphasize, before we reach yn minus 1, okay, there will be another trapezoid here. The right endpoint will be, the right base rather, will be yn minus 1 as well. Okay, so see the pattern here. y0 does not have a partner, but y1 has a twin, okay, in the next trapezoid to the right. So we can simplify this, of course, as y0 plus 2y1. And then y2 also has a twin to its right. Why is there a 1 over there? We should remove that. And yeah, that one, little typo. It's hard to see. So there will be 2 y2s as well. And then there will be 2 y3s as well. And we keep going. There will be 2 yn minus 1, but only 1 yn. Okay, because the last trapezoid, its right edge is yn. It does not have a partner. So here's the pattern. We have 1/2 of the width, delta x, and then we compute the y-coordinate over each of the x-coordinates that we found in the partitions. We double the value of the y-coordinates between y0 and yn. We don't double y0 or yn. We add it all together, multiply by 1/2 delta x. Okay, so that is the recipe that we are going to apply to the integral from 2 to 6 of cosine 1 over x dx. here we go. So first we find the width of each subintegral interval. So we take the difference of the endpoints. We have 6 minus 2. And we want 8 subintervals. So 6 minus 2 divided by 8. And of course that is equal to 1/2. Ta-da! Okay, so delta x, our delta x is 1/2 or 0.5. So we want the endpoints. So we start with x0. It is the left endpoint of our domain, so it's 2. And then we move to the right by delta x, which is 0.5. So the next endpoint is 2.5. And then after that, we move to the right by 0.5. We are at 3. Obviously, see the pattern. And our last endpoint will be at 6. Right? So to keep our work organized, let's make a little table with the endpoints, the y-coordinates, the factor that we are multiplying by each y value, and the total contribution, right? So let me set up a table for you. All right, here is our table. So we have our endpoints, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, and ending with 6. So remember, we start counting at 0, x 0, 1, 2, 3, 4, 5, 6, 7, 8. So even though n equals 8, we have 9 endpoints since we start at x0. We're going to compute the y-coordinate at each of these x-coordinates. And after we get the y-coordinate, we will multiply by the factor that appears in the trapezoid method. So the first and the last endpoints, we do not do anything. We just copy them over here. But for the points in between, we double, and that will be their contribution to the formula. Okay? So from the top, we have x equals 2. You have your scientific calculator with you. Make sure that you're in radians mode, okay? Otherwise, your answers will all be really, really close to 1 because 1/2 degree is pretty close to 0. All right, so cosine of 1/2 is approximately this much, 877. So we will put that here, and it will have its contribution over here. Okay. 2.5. What is cosine of 1 over 2.5? There should be a decimal point there. And so we're going to get this much. And we will double it here. So here's what I'm going to do. I'm going to put a times 2 there. And I'm going to put an equals there. So the first number goes into our column here. And the second number goes into our contribution column. Okay? So, yeah, if you're doing this by hand, I know it's a little bit tedious, but it's just 9 numbers. Okay, you can do it. Remember, we're going to add up all of these contributions. So let's begin a running total. At least a line that will tell us that we are going to be adding these contributions together. Okay, not this column, but this column. All right, so our next number is 3. What is cosine 1/3 radians? We have this much. We will double. We get this much. It goes here, and this goes here. And we will add it to our two other terms. Okay. 3.5 times 2 add it to our previous terms. Okay. 4 times 2 add them up. 4.5. Five. Are we there yet? Are we there yet? 5 times 2 Let me start a new line. And then we'll just add all of them together. Almost there. 5.5. Times 2. Last one. 6. And we don't do anything. And you're saying you left out one of them. Yeah, here we go. Left this one out. And the last number is 0.896. Okay, so there should be 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that is correct. So yeah, let me move this over to the next line so that we can see our subtotals for each line. Okay, so the first 5 numbers add up to this much, and the last 4 numbers add up to this much, so we will add them together like this. Of course, on your calculator, practice using the memory button. There's an M+ button or a store button. And if you don't know how to use it, there's the internet. You can find the manual to every calculator that was ever made. So that is the total of our contributions. That is not the integral though. So remember that Maple said this is approximately 3.834. Okay? So in the formula, let's scoot back down to the formula. Remember that there is a 1/2 delta x. All right? Our delta x is 1/2, so 1/2 of 1/2 is 1/4. So the integral, the approximation that we get for this integral is this total times 1/4 or divided by 4. So our approximation is going to be pretty darn close. 3.832 for us, 3.834 for Maple. Okay, so yeah, Maple is probably going to be a better answer. But again, this is what we're going to study in the next video. We got a pretty good answer, and it looks like we agreed to 2 decimal places. But who knows? Maybe we're better than Maple. Yeah, fat chance. I don't think so. Exactly how good is this approximation? So what we're going to study in the next video is what is the maximum possible error of this approximation. And if you want a better answer, you might say, you know what, I don't like that at all. That error is too big. I want to make the error at most this much. I will have to repeat this process. And of course, if I were a working engineer or whatnot, I will not be doing this by hand. I will be using a spreadsheet, some kind of computing power. How many subintervals will I need to make my estimate, my approximation, correct to the desired accuracy? All right, that's for the next video. So next we're going to look at our second method, which is Simpson's rule. All right, so here is Simpson's rule. It starts out in the same way as the trapezoid method. We will subdivide the domain into n subintervals, having the same formula for the width. Delta x is b minus a over n. But this time, n has to be an even number, and you will see why in a minute. So as before, we will locate the endpoints of the subintervals. We will call them x0 to xn, just like before. But now, in the trapezoid method, we approximated the subinterval, the integral on the subinterval x0 to x1 using a trapezoid, connecting the 4 points determined by the base, the 2 points on the base, and the 2 points x0, y0, and x1, y1. So this time, we're going to take the points 3 at a time. So we have 3 points, x0, y0, x1, y1, and x2, y2. We will string them together in a parabola. And you might think, okay, is that really possible? Yes, it basically is the result of a system of linear equations, okay? When you have 2 points with distinct x-coordinates, you know that we can draw a line through those 2 points. In the same way, by solving for the coefficients of a parabola, a, b, and c, if you have 3 points with distinct x-coordinates, x0, x1, and x2, then it is possible to find values for a, b, and c, which will form a parabola passing through those 3 points. Okay, we will see that in GeoGebra in a minute. Okay, so repeat this with, so our next 3 points will be starting at x2. So x2, y2, x3, y3, and x4, y4. Okay, so we're going to take the 3 points, starting with x2, y2, which is the right end point of this parabola. Repeat that with x2, y2, x3, y3, and x4, y4. Okay, so now you can see why the number of subintervals has to be even. Okay, the last point here is x2, y2. The last point here is x4, y4. The next triple will end with x6, y6. Okay, so those subscripts are all even, right? So let's go back to GeoGebra and let's see exactly what is going on over here. All right, so we're back where we left off, and we still have the trapezoids from the trapezoid method. So we're going to hide that. What we need are the points on the graph, right? So we did have 1, 2, 3, 4, 5, 6, 7, 8 subintervals. So we do have an even number, n equals 8, to work with. So what I was saying is we'll take the first 3 points and then we will string them together in a parabola. Okay, so you can almost see it with my cursor over here as we move. Okay, we will repeat with the next 3 points starting with x2, y2. So here, oh, check it out, those are almost collinear. So yeah, it doesn't have to be a parabola. It could be just a linear function. Okay, so next we have these 3 points, and yeah, that almost looks like a parabola, don't you think? Okay, and finally we have these 3 points. So yeah, that looks like I can string them together with a parabola. All right, so we have 1, 2, 3, 4 parabolas. Okay, so it was easy enough to find the area of a trapezoid. A parabola, not so much. Okay, so our next goal then is to find an easy way to get the area bounded by a parabola, and we're going to do it in terms of the y-coordinates of some endpoints. Back to work. Okay, so the key idea is to do it for one very special, well, one general parabola over here, but the domain is going to be special. It's symmetric across the origin. Okay, so we're going from minus h to plus h. So we are going to compute the area bounded by this parabola between minus h and h, meaning this definite integral. We will express it in terms of the y-coordinates at minus h, at plus h, and at 0, which is exactly in between. Okay, so we're going to be exploiting some kind of symmetry. At minus h, we will plug in into g, plug in 0 into g, plug in h into g to get the y-coordinates, right? So shall we do that now? If you plug in negative h here, what are you gonna get? So you'll get ah squared, and then b times minus h is minus bh, so I can erase that, minus bh, plus c. Okay, if you plug in 0, you will just get c. Right, so that's easy. You will get c. And if you plug in plus h, you will get ah squared plus bh plus c this time. So I just have to change the minuses in plus. There you go. So those are the 3 y-coordinates over negative h, 0, and positive h. Right? So y0 will be this value, y1 will be this value, y2 will be this value. So shall we? y0 and y1 and y2. So y0 will be this. y1 will be c, and y2 will be this. All right, so we are going to find this definite integral, and we will express the answer in terms of these 3 y-coordinates. Very clever. All right, so we want this definite integral. Shall we use a trig substitution or partial fractions? Just kidding. It's just a polynomial. So we have x to the 3 over 3, 1/3 ax cubed, and then x becomes x squared over 2, so 1/2 of bx squared, and then the plus c will turn into plus cx. We are evaluating from negative h to positive h. Great. So plug in h into x. So that will turn into h cubed. That will turn into h squared. That will turn into h. Subtract. Plug in negative h in here. So think about even and odd powers. Negative h cubed, the negative goes out. Negative h quantity squared, the negative goes away. Negative h times c, the negative h stays. So What changes? That should be a minus. The plus stays plus for BH squared, and that should be a minus. So, what happens to each power? 1/3 plus, minus minus is plus another 1/3. So that will turn into 2/3. Okay, what about BH squared? That's plus, but that's a minus BH squared. So the BH squared goes away. CH minus minus plus, plus CH. So that's a 2 CH. Okay, so that's great. And we have done the integral. We have the final area. However, we do want to have the answer in terms of y0, y1, and y2. And maybe h. Okay, because, check it out, there is a free h in there. So we're going to factor it out. However, there is a denominator of 3. So, a common factor of 2. And you might say, factor it out. But no, I'm going to stop you. And you're going to see why I'm going to stop you. So I'm going to take out the h, 1h, that's all I'm allowed, and the 1/3. So I'm leaving the 2 inside for the 2 terms. I'm left with ah squared, okay? And a 2, no, not a 2, but a 6, because I have a 1/3 over here. I need a common denominator. Ha ha ha. So we need a 6c. Okay. So, why did I keep the 2's inside? We are about to see. You're gonna see. And here's why. I want 2ah squared. Well, I have an ah squared here and an ah squared here. So I definitely need y0 and y2. Do I need a bh? No, the bh squares cancel. There is no b. Okay. So I want this b and that b to cancel out. Oh, guess what? What's an easier way to cancel them out? Just add them together. Minus and plus will cancel out. And when you add y0 and y2, you will get 2ah squared. Haha, and that is exactly what I need. But wait a minute. I will get only plus 2c. I need 6c. Okay? So far, okay? So far, if we add, I will take y0 and add y2. I will add y2. Then I will have, let me put parentheses, just so you can see that I have y2 over here. Then the BHs will cancel out, and we will have 2 of the AHs, which is what I need, AH squares, but I will only have 2 of the C's, so plus 2C. All right, so I still owe 4 C's. Oh, where will I get C by itself? Ha 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 ha. The Y1 only has C. All right. So we have mission accomplished. I need y0 plus y2, but I owe 4 of the c's. So I need 4 of the y1s. Ta-da! So that is the area bounded by the parabola, ax squared plus bx plus c, between negative h and positive h. So it's expressed in terms of h and the 3 y coordinates, the left, 0, and the right. So how are we going to use this to find the area of 4 parabolas, right? Because remember, when we divided into 8 subintervals, we got 4 triples of points. And then we want the parabola through each triple. Okay, so of course it would be insane to do this 3 more times. So let's go back to GeoGebra and look at what the big idea is going to be. All right, so the great idea, the great thing about that formula that we just got is that it only relies on the y-coordinates of 3 points, as long as the left and right point are symmetric across the middle point. So let's think about that with these 3 points. Okay, when we said x0, x1, x2. So the gap between 2 points is, of course, the h. Okay, so I need y0 and 4y1 and y2. Okay, does it matter that this is not 0? It says 3 over there. No, it doesn't, because we can pretend that the parabola, that this point is the origin, and the parabola goes like this. And remember, we integrated a general parabola. Okay, so this is our h, this is our negative h. I just need 4 of this y-coordinate, 1 of this y-coordinate, 4 of this, and 1 of this. Okay, so repeat the idea for the next triple of points. Again, pretend that this is the origin over here, and this is your c, and this is your negative h, and this is your positive h. So I just need h over 3, and then this y-coordinate plus 4 of this y-coordinate plus this y-coordinate. Okay, but this is y2, y3, y4, so y2 plus 4y3 plus y4. Okay, so I hope you noticed y2 appears twice. Once for the first parabola, where we have 1, 4, 1, and one more time for the second parabola, where we also have 1, 4, 1. Aha! So, third parabola, I need 1 of this y-coordinate, 4 of these, 1 of these. So again, this one gets duplicated. Last parabola, I need 1 of this, 4 of these, 1 of these. Okay, so again, this point gets duplicated. All right, so let's go back to our workroom and let's write the formula. All right, so let's recap Simpson's rule and we'll derive the formula. First step, subdivide the interval from a to b into n subintervals. N must be an even number. So the width is the same as before, b minus a over n. And this is the same as our h. That's the h that we are going to use in our formula for the area under a parabola. We will take the first 3 endpoints, x0, x1, x2, and we are going to string the points corresponding to these coordinates into a parabola. So we said that the area of that first parabola is exactly h over 3, which is delta x over 3. And the contributions are y0, 4y1, plus y2. Repeat with the next triple of points, which will be from x2, x3, and x4. So we will repeat this. The area of the next parabola is delta x over 3, but we have y2, 4y3, and y4. Okay, so we might as well keep going because we only have 2 parabolas left. Okay, so let's demonstrate the formula for n equals 8. And you can, of course, generalize for any number of subintervals, as long as it's even. So 4 gets repeated over here, and then we have 5, and then we have 6. 6 gets repeated over here, and then we have 7, and then we have 8. Whoops, Ta-da! So, just like in trapezoid rule, we can factor out the same delta x over 3 from each term. But what is left? You have y0 and 4y1. The y2 gets duplicated over here. So this gets doubled. And then we have 4y3 plus y4, but the y4 gets duplicated over here. And then we have 4y5 plus y6. The y6 gets duplicated. Finally, we have 4y7 plus y8. The y8 does not get duplicated. It's the last value in our list. Okay, so before in trapezoid rule, we saw 1, 2, 2, 2, 2, 2, 2, 2, 1, and we had delta x over 2. Okay, but for Simpsons, we want delta x over 3, and then we do 1, 4, 2, 4, 2, 4, 2, 4, 1. Okay, so notice some kind of symmetry. The first and the last factors are just 1, just like trapezoid. But as we go in, we get 4 reflected on the other side as 4, 2 reflected on the other side as 2, another pair of 4s reflected on the other side as 4. There's a 2 in the middle. Okay? And again, n has to be odd, so this is always going to be the pattern, that the middle number should be a 2. Okay, so if we had 10, n equals 10, we will have 2 y8, 4 y9s, 1 y10. And the new axis of symmetry will now be at the y6. Okay, so let's go over our last example, but this time we're going to do Simpson's rule. All right, so here we go. I just cut and pasted from our last example. This is the approximation that we got from Maple. This is the exact same table that we had for trapezoid, but we need to make changes. Okay, so the pattern is 1, 4, 2, 4, 2, 4, 1. 1, 4, 2, 4, 2, 4, 2, 4, 1. One more pair of 2 4s. Okay, so let's start with this entry. So that should be a 4, which means this has to change. So we're going to take this, and where will we do it? How about over here? I got some room over here. I'm going to take this and multiply it by 4. So we have this much. All right, so this will go over here. And like before, let's do a running total. So we have that, and we will need the first one, okay, which is, again, just factor of 1. This plus that one. Okay, so the next thing that has to change is this 2 will become a 4. So this has to quadruple. Do that over here, and let's have Maple compute that. Here we go again. And we get this much. Okay, so this turns into that, and we need to add to this, but let's not forget I also have this to account for. Okay, so we got 1, 2, 3, 4. All right, so we are up to here, and then we have to add this. And let's start another line. All right, so let's scoot down a little bit. And we have the next line where we got the 937. So this has to become a 4. and this needs to get multiplied by 4. And we get this much, which goes in here. And we'll start another line. Yeah. And we add the next number over here. And we'll take, this is the last 4. 1, 4, 2, 4, 2, 4, 2, 1. Okay, so we're going to take this number, multiply by 4, and get this, which goes in the table, and we add up here, and we add our last number, which is contribution factor of 1. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, all present and accounted for. So let's add up each line. We get this much, 12 something, and this much, we get 10 something. So we'll add those together, but let's not forget that we have, check out the formula, we have a delta x over 3. Okay, so our delta x is 1/2 like before. So 1/2 divided by 3, that's 1/6. So we will divide the total that we get by 6. Okay, let's add them up. Take this and add to this. And we get this much. All right. And then we will divide that by 6. So the approximate value of the definite integral using Simpson's rule, Simpson is thus, we'll take this and we'll divide by 6. Okay, and we get 3.83498. I'm sorry, 89. 83489, 83499. Okay, so this 8 differs from this 9. Okay, so I do believe that we are in agreement with Maple to more decimal places than we have with the trapezoidal rule. So if you were to make a bet which number is closer to the correct answer, can't say exact, I would say that Simpson's rule is probably closer to the better approximation. Okay, it's probably the better approximation. Great. So that is how you do trapezoids, the trapezoidal method and Simpson's rule. I will see you in the next video where we will talk about how accurate are these two methods. We are going to do some error analysis. So until then, I hope you enjoy the rest of your day. Okay, bye.